In the next series of lectures, we're going to talk about colligative properties and focus on these. And these are a little bit different than what we've talked about before. It's not going to matter what the chemical identity of our compound is when we talk about colligative properties. So these are going to be properties of a solution that do not depend on the chemical makeup of the molecules that are the solute particles, just the sheer number of solute particles, and that's it. Which is different than physical properties that are tied to chemical structure, right? So the difference in the value of these colligative properties will be demonstrated between the physical property that a pure substance would have and then how that physical property changes as we add a solute and create a solution to that pure substance. So things that fall into this category of colligative properties include boiling point or freezing point, vapor pressure, and osmotic pressure. These will be the ones that we cover. So these things like boiling point and freezing point, they depend on the attractive forces, the intermolecular forces between the particles. But they also depend on the solute particles occupying and replacing a solvent molecule's position in the substance. And so when we look at the boiling point and we consider all the intermolecular forces and we say, oh, well, that makes sense compared to this other one for our boiling point, we're looking at the IMFs. But then what we're doing is we're taking away some of those solvent particles and now making a solution where we put in something else as a solute. And that's going to have an impact on that attractive forces that that pure substance actually had originally when we form a solution. And so this is really going from how do IMFs work in a pure substance to what this chapter is focused on was how do these work when we have a combination of different molecules in a solution. So in general, since this is going to like these properties will be determined by the number of solute particles. First, I want to talk about, well, how do you know how many particles you have from your solute? And the answer is not always just one per chemical formula unit. So that would definitely be the case for a covalent molecule. So I'll show you here. So for sugar, um, when it's dissolved in water, the covalent bonds don't break at all just by being dissolved in water and interacting with intermolecular forces with the water molecules. And so if that's dissolved in water, the water will surround the sugar particle. There'll be dipole-dipole interactions, hydrogen bonding interactions, London dispersion forces, but it'll all be between the solvent and one solute particle at a time. Now, if instead I were to dissolve sodium chloride in water, I know that ion dipole interactions will actually dissolve the sodium chloride not as a sodium and chlorine unit together with its ionic bond intact, but separated. And so I'll have my cation completely surrounded by water molecules and my anion completely surrounded by water molecules, which means that formula unit of sodium chloride has broken up into two solute particles. Let's change color. So our ionic compounds that are soluble in water will typically create the number of solute particles that their constituent ions make up. So for sodium and chloride, we can create that chemical formula ratio. It's 1-to-1. So we'll produce one sodium and one chloride. For calcium hydroxide, when that dissolves in water, it actually creates three solute particles, the calcium plus 2 ion, and then the 2 hydroxide ions. So it's that mole ratio, right? 1 calcium to 2 hydroxide ions. So when one of those formula units is dissolved by water, water will surround a calcium and it'll surround 2 hydroxide ions, forming 3 solute particles. And so this is what we mean when we talk about the number of solute particles. We mean what are the individual things that are surrounded by the solvent rather than the chemical formula of that thing, right? Because a sodium cation will behave really differently than a chlorine ion, but both of them are going to take up space in the solvent, displacing the solvent-solvent interactions and creating solvent-solute interactions. And that's the important part. So we track this with the Van Hoft factor. It's got variable unit of lowercase I. So the theoretical Van Hoff factor would be the ratio of moles of solute particles to the moles of the formula units that are dissolved. And by formula unit, I mean something like sodium chloride. What we would write out. It shows the mole ratio of our different compounds, or sorry, our different atoms within the molecule. And then the moles of particles in solution are what are the number of particles that break up. So for something like sodium chloride, we know it'll break apart into sodium and chloride ions. So we anticipate that it'll have 2 solute particles for every 1 sodium chloride. So that would be an I expected right here that would be equal to those 2 particles that you expect to see divided by the 1 formula unit, for an expected Van Hoff factor of 2. So our calcium chloride, which will break up into 3 solute particles, will have a expected Van Hoff factor of 3. Our sugar, which we expect to just have 1 solute particle, will break up into just nothing. So it's just 1. And you can see the trend here. Our ionic compounds are forming multiple solute particles, whereas our covalent bonds aren't breaking, just our ionic ones when it's dissolved. So that's a good pattern to follow. The covalent compounds that can break apart into multiple units are usually ones that are acidic or basic, or acidic, and so it can dissociate an acidic hydrogen. And we'll go into acids and bases in a lot more detail, but we've touched on them briefly before. So that's where you'll see this exception where the covalent molecule can actually break apart. And so it's really, is it an electrolyte? Can something break apart into these charged particles for these covalent molecules that will break up into more than 1 solute particle? Okay, so those are our expected theoretical Van Hoff factors. We can measure this. And it's important what concentration we are measuring the Van Hoff factor at. And so any Van Hoff factor that's been actually measured is also going to report a concentration with it. And our actual Van Hoff factors that were measured for all 3 of these compounds are all at a 0.05 molal solution. So it's important that we're using molality here, because the temperature would impact the concentration of these particles, because it would change the volume of our solution, right? And so it's important that we work in molality when we work with colligative properties, because so much of this is dependent on volume. So when we measure these at this 0.05 molality, we see that our sodium chloride is pretty close to 2. It's 1.9. It's not exactly 2. Our calcium chloride is also not exactly 3. It's 2.8. Our sugar is a 1. So, hey, that's great. What's happening with these ones right here, where it's not exactly the same, is the ions are starting to aggregate a little bit. So these multiple, like all these particles that have positive and negative charge, if they get close to each other, they might kind of aggregate into 1 particle. And that can be very temporary. It could be lasting a longer time. So it's almost like these little tiny, like larger particles. So it means that not every single ion in the sodium chloride solid that dissolves in the water completely, not every single ion is perfectly surrounded by a cage of water molecules. Sometimes they come in contact with other ions and interact. And that's why we would see a lower Van Hoff factor, because it's really showing us that some of these particles didn't really quite separate completely, but it's a very small amount. Now, as you increase the concentration of that solute, you can expect the Van Hoff factor to decrease, because as we have more and more of these ions around, it increases the chances that they're going to run into each other and kind of stick and aggregate for a little bit of time. So we see in general that as concentration increases, our Van Hoff factor, that's our actual Van Hoff factor, will decrease.